All right, so we said with ANOVA, stands for analysis of variance. It's a little bit of a misnomer in that we're really comparing the means. Okay, we're testing to see if there's a significant difference amongst these several means that we're looking at, so 3 or more. Otherwise, we just use a difference of 2 means t-test. I ended up last lesson talking about what our hypotheses look like and how ANOVA is measuring that. Remember, our null hypothesis is that all of our population means are essentially the same. mu1 equals mu2 equals mu3, etc. equals mu4 if you had more. The alternative hypothesis, a lot of times people want to jump in and say it's like the opposite of this. So if you're saying in the null that all of them are the same, your instinct is to say as the alternative hypothesis that all of these means are different. And that doesn't have to be like that, okay? Because that's not actually the opposite, or in a mathematical sense or a probabilistic sense, the complement. If you're saying that these are all identical to each other, they are all equal, everything else, the alternative, would be that at least 2 of them are different. Not all of them are equal to each other. So we could have mu1 equal to mu2, but mu3 is different. That falls under the realm of our alternative hypothesis, that not all of them are identical to one another. And that's an important distinction to keep in mind, because remember, ANOVA is kind of like an overview of the big picture for what's going on. Okay? You get your quick p-value, you make your interpretation. Okay? Either they're all the same and I can move on to my next issue, or there is a difference and that not all of them are the same, and then this requires further inquiry. All right, where does that difference occur? What exactly is the issue here that led us to the alternative hypothesis? And we said since the beginning of the year that it's not enough to look at mean alone. If I just give you an average, okay, a lot of times in everyday life, that's sufficient for what we're talking about. But when we start comparing means or comparing averages to one another, we need to have an idea of the spread or the variation of those data sets. And I illustrated this last week with these sets of box plots, where we know box plot, we're talking median, okay, but these are symmetric data sets, so the mean and the median are all the same. And when you're comparing A to B, the first box plots have the same mean. The second box plots, same mean. Third box plots, same mean. And these are sampling distributions, right? They're built from our sample data. So for comparison, our null hypothesis is going to be saying that, like, if A is our sample, these 3 means are all identical to each other. Our alternative hypothesis is that they're not all the same. Same set of hypotheses if B was our sample data. Now, let's say that we take a set of values in our sample and compare it to our distribution, and like looking at our first box plot, we take another value and its sample mean falls like right there, kind of in line with the mean of our second box plot. Well, it's kind of within the realm of what's to be expected, and kind of goes back on the idea that we expect it to be right there at the center, but there's some variation, and life goes on. But if our data looks like set B, and within this first variety that I'm selecting, I collect my data and it comes back with a mean that's more in line with the second box plot's mean. I've been a little slanted there. in relation to the entire spread, look at how much more that differs in comparison to A. It's in line with the second group's mean, but this is like near the maximum value that it has in this case, as opposed to here we're still within that inner quartile. So when we're comparing these, okay, the samples in A contain a larger amount of variation among the sample means relative to the amount of variation within the samples. So ANOVA will find more significant differences among the means in B. If I were to run my test of ANOVA in A, these means are all essentially the same because there's a lot of spread, there's a lot of variation here. So even if I expect it to be right there and I get something here, it's all good. It's within the realm of what's to be expected. Yeah, there's a little bit of overlap. They're all essentially the same. Okay? We would fail to reject the null hypothesis here. But if our data looked like B, and everything is all very condensed right around the center, so I come in with my sample that's more in line with the mean of B, but it's part of, or the middle one, but it's more in line, it's more in line with the middle one, but it's actually a part of this first species or variety, then in that case it would be rare for us to expect this and get something there because of that variation. Okay? It's the variation, the variability amongst your data that contributes to the differences in the significance of the means. Does that make sense? So, when we're talking about ANOVA, okay, it's kind of summarized in this bullet point right here. It is one of the oddities of statistical language that methods for comparing means are named after the variance. Okay? ANOVA, analysis of variance. Okay? It's not like ANOMA or ANOME, right? Analysis of means, because it's the variance that contributes to that significance. Okay? The reason is that the test works by comparing two kinds of variation. Now, analysis of variance is a general method for studying sources of variation in responses. Comparing several means is the simplest form of ANOVA. So it gets more complicated than this. We are concentrating on one way, ANOVA. Now, last time I mentioned we are using the F distribution for our analysis. And we just let the calculator compute its F statistic and the p-value. We made some conclusions from that. P is low, reject that, null hypothesis, okay, that the means are not all the same. Now, we're going to get into a lot more detail about that F distribution here today. The way it's calculated is pretty straightforward. It's this simple ratio here. It's the variation among the sample means divided by the variation among the individuals in that sample. The challenge here is, how do we measure this variation? We're comparing those means to the variation among the individuals in the samples. Okay, so it's a straightforward comparison, but the actual calculation can be a little bit tricky. With this F distribution, we said that it is heavily skewed to the right, something like that. I think I showed it to you with GeoGebra. Our p-value is the amount of data in the tail that goes off to the right. Okay? So our F statistic that we get from the calculation of this ratio is along the x-axis here. It must be 0 or positive. And then our p-value is the data under the tail based off of that distribution. We could use a chart, or I'm going to show you how to use the calculator or GeoGebra to get that p-value if you have the F statistic. So in order to use ANOVA, it says like all inference procedures, ANOVA is valid only in some circumstances. Things that we are checking for. We need independence from each of our populations. Independent, simple, random samples. Okay? Not a surprise there. It's been a requirement. We're not going to like check statistically for like calculations of independence with multiplying probabilities or anything like that. And this is more of like a logical assumption. And in fact, for these first two bullet points, a lot of times you are just kind of assuming that they fit the mold. Yeah? At least for the types of problems that we will be doing. Second one, we need to have normally distributed data sets from our populations, which we said that normal distributions often apply to natural measurements. So measures of like lengths, remember we're talking about the flowers here, the different varieties of flowers. Those lengths are typically normal because they are natural measurements. Even if it's not perfectly normal, this can be overcome by the sample size. If you have a large sample size, it kind of throws off the essentialness of that condition. The one that is a little bit of a sticking point here is this standard deviation. All of the populations have the same standard deviation sigma, whose value is unknown. Y'all love this language here. Like, it is important. It is an important condition that they are all identical, but you don't actually know what they are. Okay, it's so bizarre sometimes like that. What ends up happening in this case is, yeah, again, you're going to use your sample standard deviation to replace that population standard deviation. And no, they're not all going to be identical. But our rule of thumb here, the results of an ANOVA F test are approximately correct when the largest sample standard deviation is no more than twice as large as the smallest sample standard deviation. Okay? So like these flowers, we're comparing 3 different varieties of flowers. Each had their own sample standard deviation. When we go back and look at our raw data, the largest standard deviation was that middle variety, which was the red. The smallest standard deviation was the yellow. So if we do big standard deviation divided by small standard deviation, we get 1.85. As long as that value is less than 2, our results should be pretty accurate. Now I will say that some of the example problems that we will see do not meet this condition. In that case, we're not going to like throw up the white flag and call it quits and say it doesn't satisfy this condition. No. What happens in that case, and if you see something like that on a test that you're taking, okay, you continue forward, but you should make note that you should proceed with caution, that these might not be completely accurate results. Okay? You need to be careful with your interpretation. In this case, with our flower example, it is less than 2. We can safely use ANOVA to compare the mean lengths for those 3 populations. So when you're checking conditions, independence, normality, standard deviations, big divided by small, hopefully it should not be bigger than 2. Now, set for that F statistic, you're looking at the variation among the sample means divided by the variation among the individuals in the same sample. So the way we measure this and the way we kind of create what this particular distribution looks like for every example is based off of the degrees of freedom. Yeah? And an F distribution actually has 2 degrees of freedom. Or no, let me rephrase that, 2 different degrees of freedom. Okay? One for our variation among the sample means, our numerator, and one for our variation among the individuals in the sample, our denominator. Okay? The rest of what we're talking about today is kind of like based off of our top and our bottom, our numerator and our denominator. We'll be referring to this as like our group and our error. And when we talk error, it's not a mistake or anything like that. It's just the label that's been used for years. So our degree of freedom calculation, they get into some complicated wording here. Essentially, we are looking at how many different ways are we breaking down our variables? How many populations are we comparing? Okay, so we have different populations that are being compared, and we also have different individuals within these populations. In our flower example, and this was our high-buy variety, this was our, or no, it was a B. This was red, and this was yellow. We had our three different sample sizes, 16, 23, 15. So our total number of observations across all three of our samples was 54. Now, we split this into three different groups, three different kinds of flowers. So that's one of our degrees of freedom. Our first degree of freedom is taking our number of breakdowns, and they use I for this, okay? And just take away one. Like instead of n minus 1, in this case it's I minus 1. Here we have 3 minus 1, or 2. Okay, so our group, our numerator degrees of freedom, our degrees of freedom for the denominator, our error, we're taking our overall number of individuals in the sample, 54, and subtracting away however many breakdowns of the sample we have. So 54, we have this high variety, the red variety, the yellow variety. Subtract away those three, we have 51. So typically this is presented two ways. It'll be like degrees of freedom, 2 comma 51, like that. First is the numerator, second is the denominator. The way this should work is if you add these two together, it will be like your n minus 1 degrees of freedom. So 54 minus 1, 53. Yep, there's that sum right there. Questions with that? Now, you will be presented with data in one of two ways. Either the raw list of data, like we saw a little bit with our flowers last time, or you'll kind of be presented with this summary chart here, where you have population 1, population 2, however many you're comparing, each of those sample sizes, the sample means, and each sample's standard deviation. This is where it gets absurdly complex that you would never in your right mind do this by hand. Okay? But what they're doing is they are finding what are called mean squares. Those are the numerator and the denominator values. Okay? So you're finding the mean squares of the group, which is the numerator, and the mean squares of the denominator, which is the error, the mean squares of the error. And essentially what's going on is you're looking at the sum of all your observations and their means, and then finding out how much each sample mean differs from this overall mean, and that contributes to the mean square for the groups, okay, MSG. you're doing a similar type of thing based off of the number of individuals that you have in the denominator. This contributes and becomes the mean square for the error, MSE. What's important and is letting the calculator do those things for us so that we can get MSG and MSE, the mean square for the groups and the mean square for the error, because MSG divided by MSE is that F statistic. Okay. Now, to do this, don't worry about those equations. Okay. If you had the raw data, you would let the calculator perform this for you. That was all of the extra stuff that the calculator gave us last week when we did our ANOVA test. All we looked at the time was F statistic and p-value. Okay, but I'll show you that in a second. All that extra stuff is what's going on here. Now, the statistical software gives you an output like this. Okay, whether it's like Minitab that the book uses or GeoGebra, if you were to do it with this, you get it spit out something like this, where it has your group and your error, the variation among the samples and the variation within the samples. Here are our 2 degrees of freedom that we talked about. And it uses the sum of the squares. That was one of those intermediate steps along the way. So you know, Pitt is looking at us to create a table like this, or be able to do something like this, where if we have the raw data, we can create this entire table, and if that were the case, you'd let the calculator or GeoGebra do it. Okay? Where you would let it perform the ANOVA test, and you just write down values in their relevant places. What's more likely is that they will give you a partially completed table like this, and you have to fill in the rest. And that's actually the more complicated one, because you're not just turning it over to the calculator. They want you to demonstrate that you have a little sense of what's going on here. Now, we have some important relationships from this chart. Ultimately, we're working towards this F statistic and p-value. But to get there, you're probably going to be provided with this, the sum of the squares. Now, that's a good value to know, because we can find the mean of our squares very easily from that. The sum of our squares, we're splitting across the degrees of freedom. So what we have up here, you take this sum of square value divided by the degrees of freedom, that is your mean of squares value, the MSG that we just saw with that incredibly complicated formula a couple slides ago. Okay. So you take that 1082.87 divided by our 2 degrees of freedom in our variation for the samples, we have 541.44. In our error group here, we had 106.57 divided by 51 degrees of freedom, MSE, we get 2.09. So when you divide this 541.44 divided by 2.09, this is our chi-square statistic. Not chi-square, our F statistic. Tests are running together here. 259.12. And you could look this up with GeoGebra, you could look it up with a chart, okay? But what we're going to do momentarily is look this up either with GeoGebra or the calculator, and it can provide you with a p-value. In this case, if you have an F statistic this big, no matter what the degrees of freedom are, this p-value is essentially 0, okay? Which is what the flower example turned out to be. That interpretation we had said last time is that we have strong and convincing evidence that these means are not all the same. Questions so far? All right. Let's try an example here. This is looking at an example problem that's comparing road rage between different age groups. And they were measuring the number of incidences that they had. We don't have the raw data in this set. However, we have our summary statistics, the sample sizes from each group, the sample means, and the sample standard deviations. Again, it helps to think, what are the null and alternative hypotheses? The null hypothesis is that all of these means are the same. 2.22, 1.33, 0.66. Okay, these are talking about average number of road rage incidents per person over the span of like 2 years or whatever this study was. Okay. The sample standard deviations, we see those as well. And it talks about the shape of our distribution in terms of meeting our conditions. And we don't exactly have the pictures of the distributions right here because we don't have the raw data, but it tells us these distributions are somewhat right skewed. And that makes sense. Because if you're saying that these means are like 2 incidents of road rage, 1 incidence of road rage, on average 0.6 incidents of road rage, there's only so far left you can go, right? You can't go beyond 0 into negative incidences of road rage. But there's probably some pretty angry drivers in each of these groups that have 10 incidents of road rage, 12 incidents that really pull that skew out to the right. We need normally distributed data for our ANOVA test to work. But they're saying that this is not really an issue here because of those sample sizes. Those are pretty substantial sample sizes, and that's like the cure-all in statistics. You have a large sample size, you can move forward. Right? It doesn't really matter about the normality because we have that large sample. Letter B, check the standard deviations that they satisfy the guideline for this ANOVA inference. Well, we have our big standard deviation is 3.11. Our small standard deviation is 1.6. So you can see that, yes, we are going to get a number that is less than 2. Yeah, 1.94. Our conclusion should be pretty accurate for this test. Even if it exceeded 2 a little bit, again, we would still move forward, but we'd probably make note of that and say that we need to proceed with caution based off of our standard deviations. Questions about that? All right. Let's take a look at this chart. Now, our degree of freedom calculations, we can do that. Our degrees of freedom for our group, we have 3 different breakdowns. And our first set of degrees of freedom is our number of breakdowns minus 1. So because we have 3 different age groups, minus 1, we have 2 degrees of freedom right there. That's the easy one. The other one, we need to look at our overall number of individuals in the samples. We need to add up all of these individuals, 244 plus 734 plus 364. We got 1342. And our 1342, that has been split across 3 different groups. So for this degree of freedom, we're taking our overall total, 1342 minus 3, we have 1339. And again, if you add these up, kind of show off here. You don't really need this number. But we would have 1341, which is our one less than our original total number. Questions there? Now, I told you that you would be provided with one of these sets of numbers, and it's usually the sum of the squares. Okay? And I wrote those in here. 356.14 for the group, 6855.68 for the error. Those values are what we got from our incredibly complicated equations on the other page, which you would not perform by hand. In this case, we need to find the mean square. And we had said that you can find this column of data by doing your sum of square dividing by degrees of freedom. So, our sum of square, 356.14, divided by our 2 degrees of freedom in the group, in our numerator, takes us to 178.07. And in our denominator, our error group, 6855.68, divided by our 1,339 degrees of freedom. So divided by 1339, we get 5.12. You don't need to work out these totals here. All right, so any questions with what happened there? Okay, I know these numbers just appeared, but again, that's what you would have. Our F statistic is calculated by MSG over MSE. Our mean squares for the group divided by mean squares for the error. So in this case, 178.07 divided by 5.12. We're looking at an F statistic of about 34.78. Now, the p-value. This is where we're going to turn it over to either GeoGebra or the calculator. Okay? Or you could look this up on an F distribution table. Okay? Let's take a quick look at GeoGebra first. All right, so in our probability calculator, here is our F distribution. And we had 2 degrees of freedom for our first one. And our second one, we had 1,339. We get a pretty distorted F distribution that we can't even see here. We know when we have an F statistic that high, we're probably going to get a p-value that's close to 0. But let's type this in here. For our value, we had 34.78. And we want to make sure that we're looking at this upper boundary because our p-value goes up to the right. Yeah, it gives us a p-value essentially 0 down here. Yeah. And I'm sorry you can't see the distribution in this case. We'll look at another one momentarily. And you saw the numbers that I had in there before for the shape of what a distribution like that looks like. If we go over to the calculator, what you can do here is the same thing without the GeoGebra. You're going to press second and distribution, which is that variables button. This has all of our tests here. If we were to analyze the shape of that distribution itself, we're going to jump down to letter 0, which is an FCDF, okay, a cumulative density function for our F distribution. PDF above, we're not looking at an individual value, we want the shaded area under that curve, a p-value. So we'll make that selection for 0. You just provide it with the area that you need to find under that curve. We had an F statistic of 34.78. So let's type in 34.78 as our lower boundary. Our upper boundary, we're just going to take that up high. Let's just make it 9999999. Okay, no need to be exact with that. We had 2 degrees of freedom for our numerator. For our denominator, okay, this is the number that's really given us extreme results like this because of our degrees of freedom, our substantial sample size. Okay, 1339, paste that in there. 1.88 times 10 to the negative 15th, you can see that's essentially 0. So in this case, reject the null hypothesis, accept the alternative hypothesis, that we did have a significant difference with the means, that they are not all the same for the number of incidents, average number of incidents of road rage for the different age groups. Anybody have any questions there? Okay. Let me flip back. All right, so as I said, for the pit final, you may be given a problem scenario like this. If you have the raw data, okay, we'll enter the data in our list on the calculator or GeoGebra, run a test of ANOVA, and you'll get all of these summary statistics. I'll walk through an example of that with you in a second. But what's more likely is that you'll have a partially completed table like this. And we fill in the blanks. We fill in what's missing. Okay? Well, let's take a look at some more practice there. On Canvas for today, I have something called like ANOVA examples or ANOVA table examples. I do have some of these printed out if you want it, if you're in class day. Who wants the paper? Anybody?
Thank you.
You're welcome. All these trees that died. All right, so let's walk through one together again. There's another one that I'll let you kind of do it on your own time, and then on the back we have a raw data set. Okay, and we'll try this, we'll practice this one together. Okay, first one. There was a small study that was done to compare head injuries in different automobile accidents based off of the size of the car. So subcompact, compact, mid-size, full-size. Each of those, we took a sample of 5 cars. And they have their own sample mean and their own sample standard deviation. So we have our blank chart here with the sum of squares provided for us. Again, that is typically the value that will be included. So what we need to do, kind of fill in the blanks of what's missing in order to complete our table. Now, off to the side, remember we have our null hypothesis that they're all the same. mu1 equals mu2 equals mu3 equals mu4. That's an equal sign, not a not equal sign. Our alternative hypothesis, they are not all equal. That is sufficient for your alternative hypothesis. Okay, so up here, we're finding our degrees of freedom. Degrees of freedom for the group, the numerator, and degrees of freedom for the error, the denominator. Remember that this is just looking at the breakdown. We have 4 different breakdowns of car. Subcompact, compact, mid-size, full size. N-1 for that. 3 degrees of freedom for the group. For the denominator and the error, we are looking at our overall total here. We have 20 in our overall sample. And from that, we need to subtract away the number of different breakdowns that we have, number of different populations. This was that n minus I, if we wanted to use the labels that they provide. So 20 minus these 4 gives us 16 degrees of freedom. And again, a good check step, add these together. 19 degrees of freedom, there's your familiar n-1, 20 minus 1 gives us the 19 total degrees of freedom, even though that doesn't really contribute to our calculations at all. Question so far? All right, so we're provided with the sum of the squares. Next thing we need to find is the mean of the squares, and again, this is calculated by sum of squares divided by the degrees of freedom in that case. So all we're doing is going with our calculator, 88,425 divided by 3, 29,475. For the error, 475, 323 divided by 16, and we get 29,707. I'll go 0.69 around that. Now, I kind of got ahead of myself. I should have looked at conditions when I started this. I started setting up the hypotheses. The independence, we just have to assume here, right? There's no real check. We have a summary set of statistics. Can't really go off of that. The normality of the distribution, again, we're making an assumption that we're good to proceed. We don't have the raw data. In our last example, where we do have some raw data, we can take a quick glimpse at the distributions there. What we can take a look at is our sample standard deviations, and we might be in trouble here, right? Sample standard deviation 242, 91. If you did 242 divided by 91, we get something bigger than 2, right? 2.66. So what that means is we don't stop here and say bigger than 2, cannot proceed. Instead, you're raising this as an issue of, well, across a small sample size like this, we didn't have standard deviations that were all essentially the same. We need to proceed with caution. That might affect our interpretation of our results. This is why it's kind of important that we verify and check those conditions. All right, jumping back into it, this F test. Remember, the F statistic, MSG divided by MSE, these numbers are pretty close to each other. 29,475 divided by 29,707.69, and we have the smaller number on top. Means that we have an F statistic of 0.992. And as you can imagine, this p-value is probably not going to be that small. If we were to do this with the calculator, we have, well, here, let me show you this with GeoGebra real fast because we'll get a good picture of the distribution. Degrees of freedom in this case, we had 3 degrees of freedom. We had 3 degrees of freedom, and for our second one we had 16. Okay, so there's a more typical shape to that F distribution. You see how it's heavily skewed to the right. Now our p-value, okay, we had an F statistic of 0.992. You can kind of see that with just where we fall. Here's 1, we're pretty much right there at 1. Our p-value is going to be all the area under the curve going to the right of that. So if I type in 0.992 and I want this right boundary, we get a p-value of 0.4216. Bigger than 0.05, fail to reject the null hypothesis that based off of our samples that we don't have any evidence that these are any different. These sample means are any different. Take a look here. So our 468, 555, 486, 537.8 across our small samples of only 5 each, okay, and our variability that we saw with our sample standard deviations, okay, that they're all essentially the same. Any questions with that? What did I have? 0.4? 0.40 was it? Let me check. 0.42. Questions? Do you feel like you would be able to do this chart based off of what's provided for you? Okay. Particularly, I'm talking to those of you who are taking the pit test. All right, we do have another problem down below where I provide you with the sample statistics and the sum of the squares. I'm going to let you try that one on your own because I want us to look at the raw data that we have for our last example, which is looking at 3 different age groups, 18 to 20, 21 to 29, 30 and older, and the average body temperature that was obtained from those samples. Okay, and we're testing to see, null hypothesis, if these means are all essentially the same, or is there really like a difference in the mean body temperature across the different age groups? Make sense? Testing that they're not all the same. Well, we have a blank chart in front of us, which we can kind of deal with because we have the raw data here. Okay? We're going to type all of our data into L1, L2, L3 on the calculator. Let the calculator take care of that. Okay? So I'm not so worried about completing the chart in this case. Now that we have more information, though, we can get more of a complete idea of what's going on in our samples, though, in terms of satisfying those conditions. Okay? So in terms of independence, yeah, whatever my body temperature is probably does not have any impact on somebody else, especially if they're obtained randomly, which they should. Okay? So that's kind of an assumption, yes. the distribution of these, this could be a little bit of a sticking point because we have small sample sizes, so it's not like we can go back and say, it's a big sample size, it's all good. Look at some of these, especially that third group. 98.6, 98.6, 97, 97.5, 97.3. Just by looking at those numbers, I don't know if your mind works like this, that doesn't look like it's normally distributed. Now, let's go over to our calculator. So I have our data entered into our lists, 3 lists, L1, L2, and L3. We could do the summary statistics for each of these just by doing stat, calculate, one var stats for L1, for L2, and L3 to look at the means and look at the sample standard deviations of each. Okay, that would be one thing that you'd want to check to verify that you're satisfying the standard deviation condition, making sure you're doing biggest sample standard deviation divided by smallest sample standard deviation. One thing to take a look at here would be a quick idea of the spread of this data. So when we are comparing these, maybe with like a little histogram, or even just a box plot. Oops. We'll go with a histogram. Okay, so there's our first set of data. That's pretty normal for a sample size of 5. That's about as good as we could hope for. For our second set, unfortunately, there's no quicker way to do this than by changing the list in there. We're going to go zoom 9. Oops. Second set, it's a little skewed to the right, okay, but that could be just based off of how they fit with the margins there. Our third set was a little bit worrisome. I put L3 in there. Zoom 9 to get a good window. That's a little bit of an issue in that it's kind of bimodal, right? We have this valley in between our two sets of data. We had like a couple of 98.6s and the others were 97s. I would say in this case, because they're not that far apart, if you looked at the standard deviations and they're all essentially the same thing, okay, that we're going to proceed here because they're not that far apart, even though they fit this kind of distinct bimodal distribution there. Okay. If you're checking conditions, you may want to show a brief little sketch of a histogram like this in order to prove your point or show your point. All right, let's do our tests. So we're going stat and over to tests, down to ANOVA. L1, comma, L2, comma, L3. Hit enter, and this is everything we need for our table, with the important ones at the very top. The F statistic and the p-value. Okay, those are the two values that we need in the top right of our table. We see our p-value here, 0.19. Fail to reject the null hypothesis. Okay, we essentially have the same means for the body temperature of these 3 age groups. But scrolling down through here, 2 degrees of freedom, a sum of squares, mean of squares. Okay? You just copy these values onto your chart. Okay? Remember that sum of squares divided by the degrees of freedom, so about 1.7 divided by 2 gives us that 0.86. Scrolling down. For the error, for that row, sum of squares there, 5.52 divided by their 12 degrees of freedom, 0.46. Yeah. And then that overall, keep saying chi-square. F statistic, 0.86 divided by the 0.46. That's where that F statistic came from, about 1.879. Any questions here? All right. So what I'd like you to try right now in our remaining 9 minutes, take a look at that second example problem on your page that we had skipped over. All right? The student's taking the state assessment. See if you can complete that chart.